Close your eyes for a moment and imagine nothing. Absolute nothing. What do you see? Maybe a dark, empty space or the silence of an endless void. But here's a question, is that really nothing? Is darkness, silence, or even emptiness truly the absence of everything? Now open your eyes, look around, the table, the phone, the water bottle. Have you ever thought about how these things, even you, came into existence? How did everything come into existence? To answer this question about everything, let's tackle a more difficult question first. What actually is nothing? This is where our journey begins, with the concept of nothing. It might seem like a simple idea, but for thousands of years, philosophers, theologians, and scientists have obsessed with its meaning. What does it mean for something to come from nothing? And perhaps most mysteriously, could the entire universe, this infinite expanse of galaxies, stars, and planets, have emerged from a state of nothingness? Today, we're diving deep into the concept of nothing. We'll explore how ancient philosophers grappled with the idea, how modern science transformed our understanding of the vacuum, and whether the universe could have been born out of nothing at all. The story of nothing began long before modern science came into the picture. It starts with the earliest thinkers, those who first questioned the nature of existence and reality. In ancient Greece, Parmenides, one of the most profound philosophers, posed a simple but radical idea. Nothing cannot exist. According to Parmenides, it was impossible for there to be such a thing as nothing. If something doesn't exist, how can we even talk about it? He believed that existence was eternal, that the universe had always been and always would be. In his view, the very concept of nothingness was a logical contradiction. Think about it. If there were ever truly nothing, how could anything ever come into being? For Parmenides, the universe couldn't have been created. It simply was eternal and unchanging. His idea challenges us to rethink our assumptions. If nothing can't exist, then maybe the universe has always existed in some form. But not everyone agreed with Parmenides. His ideas were deeply unsettling, even to other philosophers of his time. Aristotle, another giant of philosophy, believed in a different view. To Aristotle, nothingness wasn't a paradox. Instead, he saw nothing as potential, the raw possibility for something new to emerge. He believed that even in the absence of objects, there was still the potential for those objects to exist. It was like having an empty canvas before a painter begins their masterpiece. For Aristotle, this empty canvas wasn't truly nothing but a fertile ground for the universe to form. Philosophers throughout history have continued to ask, can there ever be true nothingness? If the universe came from nothing, what kind of nothing are we talking about? These are questions that not only stretch our imaginations, but challenge the very way we understand existence itself. In more modern times, thinkers like Immanuel Kant pondered the limits of human understanding. He believed that nothingness, the complete absence of anything, might be something our minds simply can't comprehend. We're so used to living in a world filled with something, matter, space, time, that true nothingness is beyond our ability to imagine. Could it be that nothingness, in the absolute sense, doesn't exist at all? Or is it possible that nothing is the source of all creation? These philosophical debates lead us to the heart of one of the greatest mysteries of all, the birth of the universe. Fast forward a few thousand years, and our understanding of nothingness has evolved dramatically. While philosophers were busy debating its meaning, science began to probe deeper, using the power of mathematics and experiments. But here's where things get weird and fascinating. For centuries, scientists thought of empty space as exactly that. Empty. A vacuum was seen as the absence of matter, the place where nothing exists. But as we moved into the 20th century, something astonishing happened. A revolution in physics changed everything. When Albert Einstein developed his theory of general relativity, he showed that space and time were intertwined. They formed a kind of fabric that could bend and stretch. This meant that space wasn't just an empty backdrop where things happen. It was an active player in the universe's story. But it wasn't until the development of quantum mechanics that our understanding of nothingness was truly turned upside down. Quantum mechanics revealed that even in the most empty parts of space, something is always happening. Imagine this: even in a perfect vacuum, where there are no atoms, no light, nothing you could possibly think of as something, there are still tiny bursts of energy popping in and out of existence. These are known as quantum fluctuations. This is what modern physics has uncovered. The vacuum is never truly empty. Even when there's no matter or energy in sight, the vacuum is filled with quantum fields, and these fields are constantly fluctuating. It's like a sea where particles can randomly appear and vanish in the blink of an eye. These fluctuations are so small and fast that we usually don't notice them, but they're real, measurable, and constantly happening. This means that empty space isn't really empty. It's alive with potential, with fleeting moments of somethingness emerging from nothing. These tiny particles, which physicists call virtual particles, exist for such a short time that they can't be directly observed, but they leave behind measurable effects. This might seem like a strange, almost magical idea, that even in the absence of matter, the universe is still buzzing with activity. But this is the reality of the quantum world. At the tiniest scales, things are constantly in motion, even when it looks like there's nothing there. So when we ask the question, can something come from nothing? Quantum mechanics gives us a surprising answer. In a sense, yes. Quantum fluctuations show us that even in a vacuum, there's always the potential for something to emerge. And this leads us to one of the most mind-blowing ideas in all of cosmology. Could the universe itself have emerged from one of these fluctuations? Now let's take this idea to its most extreme conclusion. If quantum fluctuations can create tiny bursts of energy in a vacuum, could a fluctuation on a grand scale have given birth to the entire universe? This brings us to the theory of the Big Bang, the moment when everything we know exploded into existence. For decades, scientists have worked to understand what triggered this event. What could have caused the sudden creation of all space, time, and matter? One fascinating idea comes from the realm of quantum physics. The universe itself might have been born from a vacuum fluctuation. Imagine an empty void, a vacuum without stars, without galaxies, without anything. And then, out of nowhere, a burst of energy, tiny at first but expanding rapidly, creates everything we know today. This theory suggests that our universe could be a quantum event, a massive fluctuation that emerged from what we thought was nothing. In this view, the nothing that existed before the Big Bang wasn't truly empty. It was filled with quantum potential, waiting to give birth to the cosmos. And as mind-bending as this sounds, it's not as far-fetched as you might think. In fact, some of the most brilliant physicists in the world, including Stephen Hawking and Lawrence Krauss, have explored this very idea. They've shown that the laws of physics, especially quantum mechanics and gravity, might allow for a universe to come from nothing without violating any principles of science. Hawking's work on the quantum origin of the universe proposed that space and time could emerge from a quantum state, meaning the universe didn't need a creator in the traditional sense. In a way, The universe created itself from the rules of quantum physics. Lawrence Krauss, in his book A Universe from Nothing, took this idea further. He argued that the very existence of quantum fluctuations makes it possible for entire universes to pop into existence, just like virtual particles do in the quantum vacuum. Our universe might just be one of those fluctuations, an extraordinary event where nothing gave rise to everything. So can something come from nothing? As we've seen, both philosophy and science offer different but equally mind-boggling answers. From the philosophical idea of potential to the scientific understanding of quantum fluctuations, the concept of nothing is far more complex than it first appears. What we once thought of as a vast, empty void turns out to be full of possibilities, alive with the energy and potential to create entire universes. And while we may never fully understand the true nature of nothing, one thing is clear. The story of how everything came to be is as fascinating and mysterious as the universe itself. From the philosophical musings of ancient thinkers to the cutting-edge discoveries of modern science, the concept of nothingness continues to captivate our imaginations. And as we look up at the night sky, filled with countless stars and galaxies, we're reminded that the most extraordinary story of all might just be the one that begins with nothing. Take a moment and imagine this. The entire universe, every galaxy, every star, every planet, every single atom, all packed into a space smaller than a single atom. Hard to believe, right? Well, this isn't science fiction. It's the very foundation of how our universe began, according to one of the most mind-blowing ideas in all of science, the Big Bang Theory. The Big Bang Theory is the most widely accepted explanation of how our universe came into existence. It's the story of how everything, literally everything, emerged from a tiny, infinitely dense point into the magnificent, ever-expanding universe we see today. But how did it all happen? What was this bang, and how did it set the universe into motion? Today, we're going to take you on a journey back in time, way back, almost 14 billion years ago, to the very moment when time and space itself began. Before the Big Bang, there was no universe, at least not as we understand it today. Asking what happened before the Big Bang is like asking for the direction north of the North Pole. There was no space, no time, no matter. Everything was packed into an incredibly hot, incredibly dense point called a singularity. Imagine a single point that contains all the energy, all the matter, all the potential for the universe. It's almost impossible to visualize, but this singularity was the seed of everything. Then, around 13.8 billion years ago, something extraordinary happened. At one moment there was absolutely nothing, and suddenly there was everything. In an instant, that tiny singularity exploded, an event we call the Big Bang. But don't think of it as an explosion like a bomb going off. It wasn't an explosion in space, it was the rapid expansion of space itself. In a fraction of a second, the universe expanded from the size of a single point to something billions of times larger. The Big Bang was the beginning of time, space, and everything we know. But what came next? How did this initial burst of energy turn into galaxies, stars, and planets? To understand that, we need to dive into the timeline of events that followed the Big Bang. To really understand how the universe evolved, we need to break it down moment by moment. And when I say moment, I'm talking about the tiniest fractions of a second you can imagine, because in the early universe, a lot happened in almost no time at all. Let's start at the very beginning. The Planck epoch. In the first moments after the Big Bang, literally less than a trillionth of a second, the universe was in a state we call the Planck epoch. This is the earliest period of the universe that we can theorize about. During the Planck epoch, the universe was so small and so incredibly hot, over a quadrillion degrees, that the four fundamental forces of nature, that is gravity, electromagnetism, and the strong and weak nuclear forces, were united into a single unified force. This means that everything, all the laws of physics we know today, were merged into one. But we don't fully understand what happened during the Planck epoch. Our current laws of physics, including Einstein's theory of general relativity and quantum mechanics, break down under the extreme conditions of this early universe. It's like trying to merge two puzzles that don't quite fit together. One thing we do know is that space itself was expanding rapidly. But the exact details of this epoch remain one of the biggest mysteries in cosmology. We can't look that far back because the universe was so hot and dense that no light could escape. It's like trying to see through a thick fog. But what happens next in our timeline is something we can understand a little better. The birth of the forces that govern the universe today. As the universe cooled, though cool is relative, it was still millions of degrees hotter than the core of the sun. The first of the four forces broke off from the others, that is gravity. This marks the beginning of the grand unification epoch. During this time, the other three forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remained unified. But gravity began to act on its own, shaping the very fabric of space-time. Even though we can't directly observe this period, theoretical physics allows us to piece together what might have happened. With gravity pulling things together, the universe's expansion slowed down a tiny bit, but the real game changer was just around the corner. Then something truly wild happened: inflation. At around 10 to the power of minus 36 seconds after the Big Bang, the universe went through a phase of exponential expansion. And when I say exponential, I mean mind-blowingly fast. But why did this inflation happen? The exact reasons are still a bit of a mystery, but it likely has to do with a form of energy known as the inflaton field. This energy caused space to stretch faster than the speed of light. Yes, you heard that right, faster than light, until the universe was suddenly billions of times larger than before. The good news is that as the universe expanded, it cooled down rapidly. And as it cooled, the remaining forces of nature, the strong nuclear force, the weak nuclear force, and electromagnetism, started to break apart, each acting independently. This set the stage for the formation of matter and the first particles. As inflation ended, the universe entered a new era, and things were finally starting to take shape, literally. The extreme heat and energy of the early universe began to cool just enough for the first subatomic particles to form. Quarks and gluons formed. Quarks are the building blocks of protons and neutrons, while gluons act as the glue that holds them together through the strong nuclear force. This era, called the quark epoch, saw a chaotic dance of particles smashing into each other, sometimes forming protons and neutrons, and sometimes breaking apart again. The universe at this stage was still way too hot for these particles to combine permanently. It was a cosmic soup of energy where particles flickered in and out of existence. But as the universe continued to cool, the forces holding them together became stronger, and soon these tiny particles began to stick. But how did we go from these tiny particles to atoms, stars, and galaxies? To answer that, we need to talk about a very special kind of particle, photons. By the time the universe was just 10 seconds old, something magical happened. Photons, or particles of light, began to dominate. The universe was still filled with free electrons and protons, but these photons bounced off them constantly, keeping the universe opaque. At this stage, the universe was like a thick fog, where light couldn't travel very far without running into an electron or another particle. But during the next few minutes, something extraordinary happened. The first nuclei of atoms began to form in a process called nucleosynthesis. Protons and neutrons came together to form the nuclei of hydrogen, helium, and a little bit of lithium, the lightest elements in the universe. These simple elements would eventually go on to form the building blocks of stars, planets, and everything we see today. But for now, the universe was still a hot, dense plasma where light couldn't escape. It would take hundreds of thousands of years for things to cool enough for atoms to form and for the universe to become transparent. Fast forward a few 100,000 years, and the universe had cooled down significantly, enough for electrons to combine with protons and form neutral atoms. This period is called the era of recombination, and it was a major turning point in the universe's history. Finally, for the first time, the universe became transparent. Light could now travel freely without constantly bouncing off particles. And what was left behind from this era is one of the most important pieces of evidence for the Big Bang, the cosmic microwave background radiation, a faint glow of leftover heat from the Big Bang, still detectable today. But as I explain this story, you might wonder, how do we know all of this? Well, the Big Bang theory isn't just a wild guess. It's supported by extensive evidence. Let's discuss three key pieces of evidence that make the Big Bang theory the most accepted explanation for the origin of our universe. The first one is CMBR. The cosmic microwave background radiation is often called the afterglow of the Big Bang. It's a faint radiation that fills the entire universe, and it's the leftover heat from the Big Bang itself. Discovered in 1965 by scientists Arno Penzias and Robert Wilson, this radiation is like a snapshot of the universe when it was just 380,000 years old. When scientists first detected the CMB, it was like discovering the universe's baby picture. It showed us what the universe looked like in its infancy, a hot, dense plasma, glowing with heat. Over billions of years, that glow has cooled, but it's still out there, and we can detect it using special telescopes. The CMB is one of the most compelling pieces of evidence for the Big Bang. It's a direct remnant of that early explosion, and its uniformity across the sky tells us that the universe began from a single, incredibly hot point. The next piece of evidence comes from something we call redshift. When we look at distant galaxies, we see that their light is stretched, moving towards the red end of the spectrum. This redshift is caused by the expansion of the universe. As space itself expands, it stretches the light traveling through it, making it appear redder. In the 1920s, the astronomer Edwin Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they're moving. This was one of the first clues that the universe is expanding. And if the universe is expanding now, it must have been much smaller in the past, leading scientists to theorize that the universe began from a single point, the Big Bang. Finally, last but not least, the abundance of light elements, hydrogen, helium, and lithium, provides further evidence for the Big Bang. The early universe was hot and dense enough for nuclear fusion to occur, but only for a short time. During those first few minutes, the universe produced a lot of hydrogen and helium and a tiny bit of lithium. Today, we observe that the universe is made up of about 75% hydrogen and 25% helium by mass, with only trace amounts of heavier elements. This matches the predictions of Big Bang nuclear synthesis, which tells us that the universe must have gone through a hot, dense phase where these elements were formed. So where does that leave us? The Big Bang theory tells the incredible story of how the universe came into being from a tiny, hot, dense point. From the birth of particles to the formation of stars and galaxies, the universe has been expanding and evolving for billions of years. Today, the universe is still expanding, and scientists believe it will continue to do so for billions, if not trillions of years. But one thing is clear: the story of the Big Bang is far from over. As we continue to explore the cosmos, we'll uncover more mysteries about how the universe began, and perhaps how it might one day end. From the tiniest particles to the largest galaxies, the Big Bang theory offers a glimpse into the greatest mystery of all, the origin of the universe itself. Now let's discuss cosmic inflation in detail. Imagine the entire universe just after the Big Bang, incredibly small, incredibly hot, and expanding at a pace almost beyond imagination. Now, what if I told you that in the tiniest fraction of a second, the universe expanded faster than the speed of light? What if I told you that this rapid expansion shaped everything we see today, from the stars overhead to the planets we call home? This is the story of cosmic inflation, one of the most mind-blowing concepts in all of cosmology. It's the theory that explains how the universe went from an infinitesimal point to the vast, structured cosmos we live in today. And without it, the universe as we know it wouldn't make sense. So let's discuss inflation, because we're about to dive into one of the most extreme moments in the history of the universe, a moment where everything changed in an instant. To understand cosmic inflation, we have to rewind time to just after the Big Bang, a moment known as the Planck time, or roughly 10 to the power of -43 seconds after the universe first began. At this point, the universe was unimaginably tiny, perhaps smaller than a proton, and something astonishing happened. Something that transformed this microscopic universe into the vast cosmos we know today. This event is called cosmic inflation. Inflation is the theory that in the first fraction of a second after the Big Bang, specifically from around 10 to the -36 to 10 to the -32 seconds, the universe expanded exponentially. During this brief period, the universe grew by a factor of at least 10 to the 26th power. To put that into perspective, imagine taking something the size of an atom and stretching it to the size of a galaxy in less than a trillionth of a second. And in the process, this rapid expansion set the stage for everything that followed: the formation of matter, stars, galaxies, and eventually, life. But this wasn't an explosion of matter like you might imagine. It wasn't that galaxies were flying apart. Instead, it was space itself expanding. Space stretched faster than the speed of light. And as strange as that sounds, it's perfectly allowed by the laws of physics, because nothing within space is breaking the light speed limit. It's space itself that's expanding. But cosmic inflation doesn't just describe this incredibly rapid expansion. It also helps explain some of the biggest mysteries about the universe. Mysteries that, without inflation would be hard to make sense of. To make sense, look up at the night sky. The stars seem scattered across space, but if you zoom out, way out, you'll notice something fascinating. No matter where you look in the universe, it's more or less the same. The cosmic microwave background radiation, the leftover glow from the Big Bang, has the same temperature in every direction. The distribution of galaxies is uniform. On the largest scales, the universe looks incredibly smooth and even. This might not seem strange at first, but think about it. If the universe started as a hot, dense point and expanded over time, how could different parts of the universe, parts that are billions of light years apart, be so similar? This is what scientists call the horizon problem. According to the standard Big Bang model, there hasn't been enough time for light or heat to travel between distant regions of the universe and even things out. Without inflation, those regions of space should look very different. They should be much more chaotic and disordered. But inflation solves this problem. During the inflationary period, the universe expanded so rapidly that regions of space that were once close together were stretched far apart. In other words, before inflation, all parts of the universe were in close contact. They shared the same heat and conditions, which is why today, even the most distant parts of the universe look so similar. This rapid expansion also helped smooth out any irregularities or wrinkles in the early universe. Imagine a balloon with tiny bumps on it. If you inflate that balloon really fast, those bumps get stretched out and smoothed over. That's essentially what inflation did to the early universe. It made everything more uniform. But inflation didn't just explain the uniformity of the universe. It also gave us a clue about the seeds that would eventually grow into galaxies and stars. Now you might be thinking, this sounds amazing, but is there any proof? How do we know inflation really happened? That's where things get really interesting. While inflation is still a theory, there's strong evidence supporting it. Evidence that comes from the earliest light in the universe, the cosmic microwave background, as well as detailed observations of how galaxies are distributed across the cosmos. Let's start with one of the key predictions of inflation: tiny fluctuations in the early universe. During the inflationary period, even though the universe was being stretched out, tiny quantum fluctuations, small ripples of energy, were happening at the same time. These fluctuations were microscopic, but as the universe expanded, they got stretched to cosmic scales. And these ripples in the fabric of space-time eventually became the seeds for all the structure in the universe, the galaxies, stars, and planets. These fluctuations left an imprint on the cosmic microwave background radiation. When scientists look at the CMB, they see tiny variations in temperature, tiny differences that correspond to those initial quantum fluctuations from inflation. Without inflation, these variations would be much larger or wouldn't exist at all. And the best part is that the predictions made by inflation theory match almost perfectly with the patterns we observe in the CMB. It's like seeing a fingerprint left behind from the early universe, and it's one of the strongest pieces of evidence that inflation really happened. There's another mystery that inflation helps explain: the flatness of the universe. When we look at the geometry of the universe, we see that it's almost perfectly flat. By flat, we don't mean like a sheet of paper. We mean that space isn't curved in on itself like a sphere or stretched out like a saddle. It's geometrically flat, meaning the rules of Euclidean geometry apply on the largest scales. But why? If the universe started from a random state, it should have been either curved or warped in some way. The fact that it's so flat seems incredibly unlikely unless something happened to flatten it out, and that's where inflation comes in. Inflation stretched the universe so rapidly that any initial curvature was smoothed out, just like how a crumpled piece of paper flattens when you stretch it. The rapid expansion made the universe so big that, on the larger scales, it appears flat. This flattening effect is another key prediction of inflation, and when we measure the geometry of the universe today, we see that it's flat, just as inflation predicts. Finally, let's talk about how inflation set the stage for the formation of galaxies and the large-scale structure of the universe. Remember those tiny quantum fluctuations we talked about earlier? During inflation, those small ripples were stretched across the universe, and over time, they grew into the first clumps of matter. As the universe cooled, these clumps collapsed under gravity, forming the first stars and galaxies. The large-scale structure of the universe, the way galaxies are distributed in vast clusters and filaments, matches what we'd expect if inflation happened. Those tiny ripples from inflation created the seeds for galaxy formation, and today we see that structure reflected in the cosmic web of galaxies that stretches across the universe. Without inflation, it's hard to explain how the universe ended up with the structure we see today. Inflation not only explains the uniformity of the universe, but also the tiny imperfections that eventually grew into stars, galaxies, and everything we see around us. So what is cosmic inflation? It's the theory that in the blink of an eye, the universe expanded faster than we can comprehend, an event that set the stage for everything we see today. Inflation explains how the universe became so large, so flat, and so uniform, while also giving rise to the tiny fluctuations that eventually formed galaxies and stars. And while inflation remains a theory, the evidence supporting it is strong. From the cosmic microwave background to the large-scale structure of the universe, the fingerprints of inflation are all around us. It's a reminder that even in the earliest moments of the universe, cosmic forces were at play, shaping everything that would come afterward. Inflation is one of the greatest triumphs of modern cosmology, helping us understand how the universe went from a tiny, hot, dense point to the vast, complex cosmos we live in today. As we continue to explore the universe, we'll uncover even more secrets about its origins. But for now, we can marvel at the fact that in the first fraction of a second, the universe expanded faster than we could ever imagine, and that this incredible expansion is the reason we're here today, gazing at the stars. Everything we know, all the stars, planets, galaxies, and even the atoms that make up our bodies, was once squeezed into a space smaller than an atom. And then, with the Big Bang, it all exploded into existence. But here's the question: how did this explosion of energy become the matter that makes up our universe today? This is the story of how matter came into being. It's a story of particles and antiparticles, of the cosmic battle between matter and antimatter, and of the creation of the first elements, hydrogen, helium, and a sprinkle of others, that would go on to build stars, galaxies, and life itself. In the first fractions of a second after the Big Bang, the universe was a hot, dense sea of energy, so hot that it was impossible for stable matter to exist. But as the universe expanded and cooled, something extraordinary happened. Energy began to transform into particles. You might remember from Einstein's famous equation E equals mc squared that energy can turn into matter. In the early universe, this is exactly what was happening. Energy was being converted into particles and their counterparts, antiparticles. But what does that mean exactly? For every particle that was created, an antiparticle was created alongside it. Think of it like a cosmic balance. Wherever a proton popped into existence, an antiproton would appear right next to it. For every electron, there was a positron. These antiparticles are like mirror images of their particle counterparts, but with opposite charges. But the interesting thing is that whenever a particle and its antiparticle meet, they annihilate each other, releasing a burst of pure energy. In those early moments, the universe was filled with particles and antiparticles constantly being created and destroyed. It was a chaotic dance of creation and annihilation. So how did anything survive? Why didn't the universe remain a perfect balance of matter and antimatter, leaving behind nothing but light? This brings us to one of the biggest mysteries in cosmology, the dominance of matter over antimatter. In a perfectly symmetrical universe, matter and antimatter should have wiped each other out. The universe should have been left with nothing but light, no stars, no planets, no life. And yet here we are, living in a universe that's filled with matter. So what happened? Why is there more matter than antimatter? This is one of the greatest mysteries in physics, but scientists believe that in those early moments after the Big Bang, there was a tiny imbalance, just a small fraction of a percent, where for every billion particles of antimatter, there were 1,000,000,001 particles of matter. This tiny asymmetry, this small excess of matter, meant that when most of the particles and antiparticles annihilate each other, a little bit of matter was left behind. And that tiny leftover amount is what makes up everything we see in the universe today. Think about that for a moment. If it weren't for that slight imbalance, if it weren't for that tiny difference between the amount of matter and antimatter, none of this would exist. No stars, no planets, no galaxies. The entire universe is the result of a small cosmic imperfection, a slight advantage that allowed matter to win the battle and survive. But this matter, this leftover matter, was still just a sea of particles. How did these particles come together to form the first atoms, the building blocks of everything? To understand that, we need to dive into the next phase of the universe's story, nucleosynthesis. As the universe continued to expand, it also cooled. By the time the universe was just a few minutes old, temperatures had dropped enough for something truly remarkable to happen. Particles began to come together to form the first atomic nuclei. This process is known as nucleosynthesis, the birth of the first elements. The first particles to form stable combinations were protons and neutrons, the building blocks of atomic nuclei. In the intense heat of the early universe, protons and neutrons fused together through the process of nuclear fusion, creating the nuclei of the first elements. But the universe was still incredibly hot and dense, so only the lightest elements could form. In those first few minutes, the universe was able to produce three main elements. The first one is hydrogen, the simplest and most abundant element in the universe, formed when a single proton and electron came together. Second is helium, the second most common element, formed when two protons and two neutrons fused together. And finally, trace amounts of lithium, one of the lightest metals, were created in small quantities. These three elements, hydrogen, helium, and a little bit of lithium, made up almost all of the matter in the early universe. But the interesting part is that even though these elements were created in abundance, the universe was still mostly empty space. It would take hundreds of millions of years before these simple atoms began to come together to form the first stars and galaxies. But without nuclear synthesis, without these first elements, the universe would have had no building blocks for stars, planets, or life. In many ways, the creation of these first elements was the universe's first great step toward complexity. The universe was now filled with hydrogen and helium, the two most important elements in the cosmos. Together, they would form the fuel for the first stars. But it would take time for gravity to pull these atoms together, forming vast clouds of gas that would eventually collapse to create stars. Hydrogen, being the simplest and lightest element, is still the most abundant in the universe, making up about 75% of all visible matter. Helium, the second lightest, makes up most of the remaining 25%. These two elements are the fundamental building blocks of stars, which would later go on to create the heavier elements in their fiery cores. But for now, the universe was still young, still expanding, and still cooling. And these simple atoms were waiting for gravity to do its work, waiting to come together and ignite the first stars. The story of how matter formed in the universe is one of incredible transformation. From a sea of particles and antiparticles to the dominance of matter over antimatter to the formation of the first simple elements. These early moments set the stage for everything that would follow. But the universe's journey was far from over. The hydrogen and helium created during nuclear synthesis would go on to fuel the first stars, which in turn would forge the heavier elements like carbon, oxygen, and iron, the elements needed to build planets, oceans, and life itself. And as those first stars ignited, the universe lit up for the first time, ending the cosmic dark ages and beginning the next chapter in the story of creation. In those early moments, the universe laid down the foundation for everything. From the particles that emerged from the Big Bang to the first elements created in the fiery crucible of nucleosynthesis, this is the story of how the universe built itself from the ground up, one particle at a time. And this journey, from the first particles to the first stars, is just the beginning. The story of the universe continues, and as we explore the formation of galaxies, planets, and life itself, we'll see just how complex and beautiful the cosmos truly is. When we look up at the night sky, we'll see a dazzling display of stars scattered across the cosmos. But how did those stars come to be? How did these fiery balls of light form from the dark, cold void of space? This is the story of how stars, the engines of the universe, are born, how they live, and how they die in spectacular explosions that light up the cosmos. And beyond the stars, we'll explore the formation of galaxies, the grand cities of stars, gas, and dust that make up the large-scale structure of the universe. From the swirling chaos of gas clouds to the gravitational forces that bind entire galaxies together, the story of star and galaxy formation is a tale of cosmic evolution, a journey from chaos to order, from birth to death, and from simplicity to the breathtaking complexity we see in the universe today. Stars are born in some of the most beautiful and mysterious places in the universe called stellar nurseries or nebulae. These are vast clouds of gas and dust spread across the galaxy, sometimes stretching for light years. But here's the thing, these nebulae aren't static. Something extraordinary happens within them. Slowly, over millions of years, these clouds of gas begin to collapse under their own gravity. As gravity pulls the gas and dust together, the material in the center of the cloud gets hotter and denser. The particles collide and compress, creating a protostar, a baby star. It's still not hot enough to shine like the stars we see in the night sky, but the process has begun. As the gas cloud continues to collapse, the core of the protostar gets denser and hotter, until one day something miraculous happens: nuclear fusion ignites. When the core reaches temperatures of about 10 million degrees Celsius, hydrogen atoms begin to fuse together, creating helium and releasing an enormous amount of energy. This energy pushes outward, counteracting the force of gravity, and the star stabilizes. This is the moment when a star is truly born. For millions, sometimes billions of years, the star will live in this delicate balance, a constant tug-of-war between the force of gravity pulling inward and the energy from nuclear fusion pushing outward. But this is only the beginning of a star's journey. As we'll see, stars live complex lives, and their fates depend on how massive they are. Most stars spend the majority of their lives as main sequence stars. This is the stable phase of a star's life, where nuclear fusion of hydrogen into helium powers the star. Our Sun, for example, is a main sequence star, and it's been burning for about 4.6 billion years. But the mass of a star determines how long it will live. Smaller stars, known as red dwarfs, burn their fuel slowly and can last for trillions of years. Larger stars, however, burn through their fuel much faster, living for only a few million years before they exhaust their hydrogen supply. But what happens when a star runs out of fuel? The answer depends on the star's mass, and it's here that the fate of a star takes one of two paths. One that leads to a peaceful death, and another that ends in one of the most violent events in the universe. For stars like our Sun, low to medium mass stars, the end is gentle. When these stars run out of hydrogen to burn, their cores contract under the force of gravity while the outer layers expand, turning the star into a red giant. During this phase, the star sheds its outer layers into space, creating a beautiful planetary nebula. All that remains is the hot core, which cools and fades over time, becoming a white dwarf, a small, incredibly dense object about the size of Earth, but with the mass of the Sun. Eventually, this white dwarf will cool and fade away into darkness, becoming a black dwarf. For these stars, their death is quiet, a gradual fading into the night. But for much larger stars, the story is quite different. Their lives end in a spectacular, violent explosion, one that lights up the universe in a brilliant flash of light and energy. Massive stars, those much larger than our Sun, live fast and die young. When these stars run out of hydrogen, they begin to fuse heavier elements like helium, carbon, and even iron. But once they start fusing iron, something catastrophic happens. Iron can't release energy through fusion, and without the outward pressure of fusion to counteract gravity, the core collapses in on itself in a fraction of a second. This triggers a supernova, a titanic explosion that blasts the outer layers of the star into space, creating some of the brightest events in the universe. Supernovae are more than just spectacular explosions. They are the factories of the universe. During a supernova, elements heavier than iron like gold, silver, and uranium are created. These elements are scattered across space, seeding the next generation of stars and planets with the building blocks of life. But the story doesn't end with the explosion. What's left behind after a supernova depends on the mass of the star's core. If the core is between 1.4 and 3 times the mass of the Sun, it collapses into a neutron star, an object so dense that a teaspoon of its material would weigh more than 1 billion tons. Neutron stars are extreme. They spin rapidly and some become pulsars, beaming intense radiation into space. But if the core is even more massive, it collapses further, forming one of the most mysterious and terrifying objects in the universe, a black hole. Here, gravity is so strong that not even light can escape, and the star's matter is crushed into a single point called a singularity. The death of a massive star is the birth of some of the most extreme objects in the universe. From neutron stars to black holes, these remnants are a testament to the incredible power and violence of the universe. But while stars have their own individual life cycles, they don't exist in isolation. Stars come together to form galaxies, vast cosmic cities that evolve and interact over billions of years. To understand the universe on a grand scale, we need to look at how galaxies form and how they've shaped the cosmos into what we see today. Galaxies are the cosmic cities of the universe, massive collections of stars, gas, dust and dark matter held together by gravity. The Milky Way, the galaxy we call home, is just one of trillions of galaxies in the universe. But how did these majestic structures come into being? The formation of galaxies began early in the universe's history when the first stars were born. But stars didn't form in isolation. They were born within giant clouds of gas that clumped together under the influence of gravity. As these clouds continued to collapse, they formed rotating disks of gas and stars, the early stages of galaxies. But there's another crucial player in galaxy formation: dark matter. Dark matter doesn't emit light, but its gravitational influence is enormous. In fact, dark matter makes up the majority of the mass in galaxies, acting like a cosmic scaffold that helps pull together gas and stars to form galaxies. Without dark matter, galaxies wouldn't have enough gravity to hold themselves together. It's like the invisible glue that keeps the structure of the universe intact. Over billions of years, these gas clouds formed the first proto-galaxies, which slowly evolved into the galaxies we see today. Some galaxies, like the Milky Way, formed spiral arms, while others, like elliptical galaxies, formed into more spherical shapes. But galaxy formation didn't happen in isolation. Galaxies interact, collide, and merge over time, shaping their evolution. When galaxies merge, their gas clouds collide, triggering bursts of star formation. Some of the most beautiful and dynamic galaxies we see today, starburst galaxies, are the result of these interactions. In fact, our very own Milky Way is on a collision course with the Andromeda galaxy, which will occur in about 4 billion years. When they collide, the two galaxies will merge to form a new, larger galaxy, changing the night sky forever. But even as galaxies evolve and merge, they are bound together by the cosmic web, an enormous interconnected structure of galaxies and dark matter that spans the universe. Galaxies don't exist in isolation. They are part of a much larger structure, the cosmic web. This web is made of galaxies, gas and dark matter, all connected by vast filaments that stretch across the universe. It's like a giant cosmic tapestry, with galaxies acting as the threads that weave the universe together. The formation and evolution of galaxies is one of the most important processes in the universe, shaping the large-scale structure of everything we see. And within these galaxies, stars are born, live and die, continuing the cosmic cycle of creation and destruction. From the gravitational collapse of gas clouds to the fiery birth of stars, from the death of massive stars in supernovae to the majestic formation of galaxies, the universe is a dynamic, evolving system. Stars and galaxies are the building blocks of the cosmos, and their formation is a story of gravity, fusion, and cosmic interactions. The universe is constantly evolving, with stars being born and dying, galaxies colliding and merging, and dark matter holding it all together. It's a cosmic dance that has been unfolding for billions of years, and it's still happening today. The next time you look up at the night sky, remember, every star, every galaxy, and every point of light is part of this grand story, the story of how the universe came to be and how it continues to evolve, shaping the cosmos into the vast and wondrous place we call home. Stars, galaxies, planets, bright points of light scattered across the vast expanse of space. But what if I told you that everything you can see, every star, every galaxy, every planet, is only a small fraction of the universe? What if I told you that most of the universe is made up of something invisible, something we can't see, can't touch, but whose effects we can feel? This is the story of dark matter and dark energy, two of the most mysterious and elusive forces in the universe. Together, they make up 95% of the universe, and yet we know almost nothing about them. Dark matter is the invisible glue that holds galaxies together, while dark energy is the force that's causing the universe to expand at an ever-accelerating rate. Let's start with dark matter. Imagine a galaxy, a massive collection of stars, gas, and dust, all held together by gravity. You might think that the stars in the outer regions of the galaxy would move slower than the ones near the center, just like planets in our solar system move slower the farther they are from the sun. But when scientists started measuring the speed of stars in the outer parts of galaxies, they found something surprising. These stars were moving way too fast, so fast, in fact, that if the only thing holding them together was the gravity of visible matter, they should have been flung out of the galaxy long ago. So what's going on here? Why aren't these stars flying away? The answer, scientists realized, is that there must be something else, a huge amount of invisible matter surrounding the galaxy, providing extra gravity to keep everything in place. This mysterious, unseen substance is what we now call dark matter. But here's the thing, dark matter doesn't interact with light. We can't see it, we can't touch it. It doesn't emit, absorb, or reflect any kind of electromagnetic radiation. The only way we know it's there is because of its gravitational effects. The first hints of dark matter came in the 1930s, when astronomer Fritz Zwicky was studying a cluster of galaxies called the Coma Cluster. He noticed that the galaxies within the cluster were moving far too quickly to be held together by the gravity of the visible matter alone. Zwicky proposed that there must be some invisible mass, what he called dark matter, holding the cluster together. Later in the 1970s, astronomer Vera Rubin confirmed this idea by studying the rotation curves of individual galaxies. She found that stars far from the center of galaxies were orbiting at almost the same speed as stars near the center, something that could only be explained if there was a massive halo of dark matter surrounding the galaxy. But it's not just galaxies that reveal the presence of dark matter. We also see its effects in gravitational lensing, where light from distant objects is bent as it passes through regions of space filled with dark matter. This bending of light allows us to map the distribution of dark matter, even though we can't see it directly. Today, dark matter is one of the biggest mysteries in astrophysics. We know it makes up about 27% of the universe, and yet we still don't know what it's made of. Some scientists believe it could be composed of exotic particles called WIMPs, weakly interacting massive particles, while others propose axions or other unknown particles. But so far, dark matter has eluded direct detection. Despite its invisibility, dark matter plays a crucial role in the formation and structure of galaxies. Without it, the universe as we know it wouldn't exist. In the early universe, shortly after the Big Bang, the cosmos was filled with a hot, dense soup of particles. But as the universe expanded and cooled, tiny fluctuations in density, caused in part by quantum fluctuations during the inflationary period, began to grow. These fluctuations would eventually become the seeds of galaxies and galaxy clusters. Here's where dark matter plays its critical role. Dark matter, with its gravitational pull, helped these fluctuations grow larger. Unlike regular matter, dark matter doesn't interact with radiation, so it could clump together early on, forming dark matter halos, the invisible scaffolding around which galaxies would later form. As these dark matter halos grew, they pulled in regular matter, hydrogen and helium gas, that would eventually collapse to form the first stars and galaxies. Without dark matter, these structures might never have formed. Its gravitational influence provided the foundation for the cosmic web, the large-scale structure of the universe, with galaxies connected by vast filaments of dark matter. In modern galaxies, dark matter continues to play a crucial role. It forms an invisible halo around galaxies, providing the extra gravity needed to hold them together, and allowing stars in the outer regions to move faster than they otherwise would. In galaxy clusters, dark matter makes up the majority of the mass, binding entire clusters together. Without dark matter, these massive structures wouldn't be able to hold themselves together. Their gravitational pull would simply be too weak. So even though we can't see dark matter, its fingerprints are all over the universe. It shapes galaxies, binds galaxy clusters, and forms the cosmic web that structures the universe on the largest scales. But while dark matter pulls things together, there's another, even more mysterious force that does the opposite. It pushes everything apart, and it's causing the universe to expand faster and faster. This force is called dark energy, and it's even stranger than dark matter. For most of human history, we assumed that the universe was static, that the stars and galaxies were fixed in place. But in the early 20th century, Edwin Hubble made a revolutionary discovery. The universe is not just expanding, in fact it's accelerating. He found that galaxies were moving away from us, and the farther away they were, the faster they were receding. This led to the idea of the Big Bang, the notion that the universe had a beginning and has been expanding ever since. But here's the twist. Scientists expected that the expansion of the universe would slow down over time due to the gravitational pull of all the matter in the universe. After all, gravity pulls things together, right? So, over billions of years, the expansion should gradually decelerate. But when scientists began measuring the expansion of the universe in the late 1990s, they found something completely unexpected. The expansion wasn't slowing down, it was speeding up. The universe was expanding faster and faster, as if some mysterious force was pushing everything apart. This force is what we now call dark energy, and it's one of the greatest mysteries in cosmology. Dark energy makes up about 68% of the universe, and yet we have almost no idea what it is. We know that it's causing the accelerated expansion of the universe, but its nature is still completely unknown. The evidence for dark energy comes from multiple sources. One of the key pieces of evidence comes from observations of Type 1a supernovae, exploding stars that are used as standard candles to measure distances in the universe. When scientists looked at distant supernovae, they found that they were fainter than expected, indicating that the universe's expansion was accelerating. In addition to supernovae, the cosmic microwave background also provides evidence for dark energy. By studying the tiny fluctuations in the CMB, scientists can measure the geometry of the universe and calculate the amount of dark energy needed to explain the accelerated expansion. Today, dark energy remains one of the biggest puzzles in physics. It seems to act like a kind of anti-gravity, pushing galaxies apart instead of pulling them together. But what is dark energy exactly? Where does it come from? These are questions that scientists are still trying to answer. There are several competing theories about what dark energy might be. One of the most popular ideas is that dark energy is related to something called the cosmological constant, an idea first proposed by Albert Einstein. When Einstein was developing his theory of general relativity, he initially believed the universe was static, so he added a term to his equations, the cosmological constant, to balance the effects of gravity. Later, when Hubble discovered that the universe was expanding, Einstein abandoned the idea, calling it his biggest blunder. But today, the cosmological constant has made a comeback. Many scientists believe that dark energy might be this constant, a kind of energy inherent to space itself, causing it to expand over time. Another theory is that dark energy could be a dynamic force, a field that changes over time. This idea is called quintessence. Unlike the cosmological constant, which remains the same throughout the universe's history, quintessence could vary in strength, evolving as the universe expands. There are even more exotic theories, like the idea that dark energy could be a manifestation of extra dimensions, or a sign that general relativity breaks down on cosmic scales. Right now, we don't know which of these theories is correct, if any. Dark energy remains one of the greatest mysteries in the universe, and solving it could revolutionize our understanding of physics and the cosmos. Dark matter and dark energy, the invisible forces that shape our universe, are among the greatest mysteries in modern science. Dark matter holds galaxies together, forming the cosmic web that structures the universe, while dark energy drives the accelerated expansion of space, pushing galaxies apart. Together, they make up the vast majority of the universe, and yet we can't see or touch them. We only know they exist because of their effects, the subtle hints they leave behind in the movement of galaxies, the bending of light, and the expansion of space. As we continue to explore the universe, we'll uncover more clues about these hidden forces. But for now, They remain the dark side of the universe, the invisible yet powerful forces that shape everything we see, and perhaps even the fate of the universe itself. Imagine for a moment the universe as it was just after the Big Bang, hot, dense, and filled with a chaotic soup of particles. In those early moments, there were no stars, no galaxies, just a sea of energy and subatomic particles waiting for something extraordinary to happen. Fast forward nearly 14 billion years, and that same universe is now filled with beautiful, majestic structures. Galaxies, clusters of galaxies, and the immense cosmic web that stretches across the universe. But how did we go from that hot, chaotic beginning to the cosmic masterpiece we see today? This is the story of the evolution of the universe. A journey that began with the first galaxies, shaped by the powerful forces of gravity, dark matter, and dark energy. Along the way, supermassive black holes formed at the hearts of galaxies, playing a pivotal role in their evolution. And through it all, the universe has continued to expand, evolving from its fiery birth into the grand, complex tapestry we see today. In the beginning, the universe was nearly uniform, with only tiny fluctuations in density. These fluctuations, left over from the inflationary period shortly after the Big Bang, became the seeds of cosmic structure. Under the influence of gravity, these denser regions began to collapse, pulling in gas and dark matter, forming the first galaxies. About 400 million years after the Big Bang, the universe entered a period known as the Epoch of Reionization. This was a turning point in cosmic history, when the first stars and galaxies began to shine, lighting up the universe for the first time. These early galaxies were small and chaotic, made up of young, massive stars burning brightly in a sea of gas and dust. But as these first stars ignited, their intense radiation began to ionize the surrounding gas, transforming the dark, neutral universe into one filled with light. This reionization process allowed light to travel freely through space, clearing the way for the universe to evolve. These early galaxies were just the beginning. Over the next few billion years, galaxies grew larger and more complex. Small galaxies merged to form bigger ones, and star formation accelerated, filling the universe with light and life. But it wasn't just stars and gas that shaped the cosmos. Dark matter played a crucial role as well. Dark matter helped shape galaxies and large-scale structures. Without it, galaxies wouldn't have had enough gravity to hold themselves together. Dark matter provided the extra gravitational pull needed to bind galaxies into clusters and clusters into superclusters, forming the cosmic web, the large-scale structure of the universe. As dark matter halos grew, they pulled in regular matter, gas and dust, that would eventually collapse to form stars. This interaction between dark matter and regular matter allowed galaxies to grow and evolve into the diverse structures we see today. The universe has been changing and evolving for nearly 14 billion years. Over time, galaxies have grown larger and more complex, and the universe itself has expanded dramatically. But the story of the universe isn't just about growth. It's about constant change, driven by the powerful forces of gravity, dark matter, and dark energy. In the early universe, galaxies were small, chaotic, and filled with hot young stars. But over billions of years, these galaxies merged and collided, forming larger, more stable structures. Mergers between galaxies triggered bursts of star formation, and over time, galaxies settled into the diverse shapes we see today: spirals, ellipticals, and irregular. One of the most dramatic events in the life of a galaxy is a collision with another galaxy. When galaxies collide, their stars pass by each other relatively undisturbed, but the gas and dust within the galaxies interact, creating massive bursts of star formation. These interactions can lead to the formation of new galaxies, larger, more complex structures that continue to evolve over time. In fact, our own galaxy, the Milky Way, has had a series of mergers throughout its history. In a few billion years, it will collide with our neighboring galaxy, Andromeda, forming an even larger galaxy. These mergers and collisions are part of the ongoing evolution of the universe. As galaxies merge, they grow in size, but they also lose some of their original structure. Spiral galaxies, for example, can merge to form elliptical galaxies, which are more spherical in shape and contain older, cooler stars. But while galaxies have been growing and merging, something else has been happening in the background, something that is affecting the entire universe. The universe has been expanding ever since the Big Bang, and over time this expansion has accelerated, driven by a mysterious force known as dark energy. Today, galaxies are moving away from each other at an ever-increasing rate. This accelerated expansion means that over billions of years, distant galaxies will drift farther and farther apart, and eventually some will become so far away that their light will never reach us. The universe is getting larger, and the vast cosmic distances between galaxies are growing. This accelerating expansion is shaping the future of the universe, but it's also a reminder of how far the universe has come. From the first small chaotic galaxies, the universe has grown into a vast complex cosmic web, with galaxies, clusters and superclusters forming the backbone of the cosmos. But while galaxies evolve and change, there's another force that has been quietly shaping them from within: supermassive black holes. At the heart of almost every massive galaxy lies a monster, an object so dense, with gravity so strong, that not even light can escape its pull. These are supermassive black holes, and they play a central role in the evolution of galaxies. Supermassive black holes are enormous, millions, even billions of times more massive than our Sun. They sit at the center of galaxies, pulling in gas, dust, and even stars. As material falls toward the black hole, it forms an accretion disk, heating up and glowing brightly as it spirals inward. These black holes are incredibly powerful, and when they're actively pulling in material, they can outshine the entire galaxy they reside in. But supermassive black holes don't just consume, they also shape their galaxies in profound ways. When a black hole is actively feeding on gas and dust, it can release enormous amounts of energy in the form of powerful jets and winds. These jets can push material out of the galaxy, regulating the rate of star formation and even shaping the galaxy's structure. In the early universe, when galaxies were smaller and more chaotic, supermassive black holes played a crucial role in regulating the growth of galaxies. By pushing out gas and dust, black holes prevented galaxies from forming too many stars too quickly, helping to maintain a delicate balance between star formation and galaxy growth. Over billions of years, as galaxies merged and grew larger, their central black holes also grew, consuming more material and becoming even more massive. Today, supermassive black holes are thought to be present in nearly every large galaxy, and their influence continues to shape the evolution of galaxies. In fact, the mass of a galaxy's central black hole is often correlated with the size of the galaxy itself, suggesting that the two have evolved together over cosmic time. One of the most dramatic examples of a supermassive black hole's power is a quasar, an incredibly bright, active galactic nucleus powered by a supermassive black hole. Quasars are among the most powerful objects in the universe, capable of outshining entire galaxies. In the early universe, quasars were much more common, as galaxies were still young and full of gas for the black holes to consume. These brilliant beacons are visible from billions of light years away, and they provide us with a glimpse into the early universe, when supermassive black holes were growing rapidly and shaping their galaxies in profound ways. The evolution of the universe is a story of growth, change, and transformation. From the first small, chaotic galaxies to the grand cosmic structures we see today, the universe has been shaped by the powerful forces of gravity, dark matter, and dark energy. Galaxies have grown larger and more complex over billions of years, merging and colliding, forming clusters and superclusters, and evolving into the diverse structures that fill the universe. Supermassive black holes have played a pivotal role in this evolution, regulating star formation and shaping the structure of galaxies. As the universe continues to expand, its evolution is far from over. Galaxies will continue to merge, stars will continue to be born and die, and the large-scale structure of the universe will continue to grow and change. The universe is a dynamic living system, constantly evolving and shaping itself. From the first galaxies to the cosmic web, the universe's evolution is a testament to the beauty and complexity of the cosmos. A journey that began nearly 14 billion years ago and continues to unfold before our eyes. The place we call home, this solar system filled with planets, moons and life, didn't just pop into existence. It had a beginning, a formation and a chaotic past filled with violent collisions, swirling gas and fiery energy. Billions of years ago, our solar system was born from the remnants of dead stars, shaped by the forces of gravity and time. And from that swirling chaos, something remarkable happened. The sun ignited, planets formed, and one of those planets, Earth, became the cradle of life. Let's take a closer look at how the solar system formed, how the planets came to be, and why Earth is so uniquely suited to support life. We'll also explore the theories that help us understand how planetary systems like ours form across the universe. About 4.6 billion years ago, the solar system was nothing more than a giant cloud of gas and dust, a solar nebula left over from the explosion of a massive star. This cloud drifted through space, quiet and unremarkable, until one day something changed. A nearby supernova, perhaps a massive star exploding, sent shockwaves through the nebula, causing it to collapse under its own gravity. As the nebula collapsed, it began to spin. The faster it spun, the more it flattened into a disk, with the majority of the material collecting at the center. Over time, the gas and dust in this disk clumped together, forming the seeds of planets and moons. But something much more dramatic was happening in the center of the disk. As the gas compressed under its own gravity, it grew hotter and hotter until at the heart of the disk, a nuclear reaction ignited, the birth of our sun. The sun's ignition marked the beginning of our solar system. Its immense gravity pulled in the surrounding gas and dust, and over millions of years, this material began to coalesce into planetesimals, small rocky bodies that would eventually grow into planets. But the process wasn't peaceful. The early solar system was a chaotic, violent place, with planetesimals colliding and merging, sometimes smashing each other to pieces, sometimes forming larger and larger bodies. Over time, 4 small rocky planets formed close to the Sun: Mercury, Venus, Earth and Mars, while further out, the gas giants Jupiter and Saturn and the ice giants Uranus and Neptune began to take shape. The inner planets, Mercury, Venus, Earth and Mars, formed from the heavy elements that were left behind near the Sun after the lighter gases were blown away by the solar wind. These planets are made mostly of rock and metal, and their formation was a slow, violent process of accretion, small planetesimals colliding and sticking together over millions of years. Each collision added more mass to the forming planets, and over time these rocky worlds developed solid surfaces and atmospheres. While Venus and Mars would eventually take very different paths, Earth was on its way to becoming a very special world with just the right conditions for life. Further out in the solar system, beyond the frost line, the point where temperatures were cold enough for volatile compounds like water, methane and ammonia to condense into solid ice, the gas giants were forming. These massive planets, Jupiter, Saturn, Uranus and Neptune, began as rocky cores, but their immense gravity allowed them to capture vast amounts of gas from the solar nebula, growing into the giants we see today. Jupiter, the largest planet in our solar system, grew so massive that it may have prevented other planets from forming in the outer solar system. Its immense gravity influenced the orbits of nearby objects, shaping the structure of the solar system as a whole. But while the formation of these planets was a spectacular event in its own right, something even more remarkable was happening closer to home. Earth was about to become a truly unique world. Among all the planets in the solar system, Earth stands out as something truly special. It's the only planet known to harbour life, and it's been our home for billions of years. But what makes Earth so unique? Why is it the only planet in the solar system, so far as we know, that can support life? The answer lies in a combination of factors that have worked together to make Earth the perfect cradle for life. From its distance from the Sun to its atmosphere, magnetic field and water, Earth has the right ingredients in just the right amounts. One of the most important reasons Earth is habitable is its location in the habitable zone, the region around a star where temperatures are just right for liquid water to exist. Earth orbits the Sun at an average distance of about 93 million miles, placing it in the Goldilocks zone. Not too hot, not too cold, but just right for water to stay in its liquid form. This distance allows Earth to have liquid water, a crucial ingredient for life. On planets like Venus, which is too close to the Sun, water would evaporate, while on Mars, which is further from the Sun, water would freeze. But on Earth, water exists in all three states, liquid, solid and gas, creating the perfect conditions for life to thrive. Another key factor that makes Earth habitable is its atmosphere, a blanket of gases that protects the planet from harmful radiation and helps regulate temperature. The planet also has a magnetic field generated by the movement of molten iron in Earth's core that shields the planet from the Sun's harmful solar wind. Without this magnetic field, the solar wind would strip away the atmosphere, leaving Earth exposed to the harshness of space, much like Mars. Perhaps the most important ingredient for life on Earth is water. Earth is often called the blue planet because more than 70% of its surface is covered by oceans. Water is essential for all known forms of life, and Earth is the only planet in the solar system where liquid water exists in such abundance. But Earth's habitability is also maintained by its geological activity. The movement of Earth's tectonic plates plays a critical role in recycling nutrients and regulating the planet's temperature. This process, known as plate tectonics, helps maintain Earth's long-term climate stability, which has allowed life to thrive for billions of years. Earth is a delicate balance of many factors: its location in the habitable zone, its protective atmosphere and magnetic field, its abundant water, and its geological activity. Together, these factors have created a world where life can not only survive, but flourish. But how did Earth and the other planets form in the first place? To understand that, we need to explore the theories of planetary formation. The formation of planets is a complex process that has fascinated scientists for centuries. Today, we have a deeper understanding of how planets form, thanks to observations of other planetary systems and advances in computer simulations. But how exactly do planets form from the dust and gas of a nebula? There are several theories that help explain the formation of planets, but the most widely accepted model is the nebula hypothesis, which describes how planets form from the leftover material in a protoplanetary disk after a star is born. The nebula hypothesis suggests that planets form from the leftover gas and dust in a protoplanetary disk, the disk of material that surrounds a newly formed star. As the gas and dust orbit the star, small particles begin to collide and stick together, forming planetesimals, small solid bodies that are the building blocks of planets. Over millions of years, these planetesimals continue to collide and merge, eventually forming larger and larger bodies, protoplanets, which will go on to become full-fledged planets. This process of accretion, where small particles stick together to form larger objects, explains how rocky planets like Earth and Mars formed close to the Sun, while gas giants like Jupiter and Saturn formed further out, where more gas was available. For gas giants like Jupiter and Saturn, the formation process may have been a bit different. One theory, known as core accretion, suggests that gas giants started as large rocky cores, which then pulled in vast amounts of gas from the surrounding disk, forming their thick atmospheres. This process is slower and works best for planets that form far from the Sun, where gas is more abundant. Another theory, called disk instability, suggests that gas giants might form more quickly through the collapse of dense regions of gas within the protoplanetary disk. This process would create massive gas planets in a much shorter time, explaining how gas giants like Jupiter could have formed before the solar wind blew away the remaining gas in the disk. Today we can observe other planetary systems forming around distant stars thanks to powerful telescopes like the Atacama Large Millimeter Submillimeter Array and the James Webb Space Telescope. These observations have confirmed that planets are forming in similar ways throughout the universe, with protoplanetary disks swirling around young stars and planetesimals colliding to form planets. These observations help us refine our theories of planetary formation and confirm that our solar system's formation was not a unique event, but part of a much larger process that happens throughout the universe. The formation of the solar system was a journey from chaos to order, from the swirling gas and dust of a solar nebula to the fiery birth of the Sun to the violent collisions that formed the planets. The solar system's story is one of incredible transformation. Over billions of years, the planets settled into their orbits, each unique, each shaped by the forces of gravity, gas, and time. And among all the planets, Earth emerged as a special world, with the perfect conditions for life to thrive. Today we are part of this cosmic story, living on a planet that formed through the same processes that shaped the entire solar system. As we continue to explore our own solar system and discover new planetary systems beyond, we're reminded that the forces that shaped our home are the same forces at work throughout the universe. For as long as humans have gazed up at the stars, we've wondered, are we alone? Is Earth the only place in the universe where life exists? Or could there be other planets, other worlds, where life has taken hold? It's a question that has fascinated philosophers, scientists, and dreamers for centuries. But today, with powerful telescopes and new technologies, we are closer than ever to finding out the answer. The search for extraterrestrial life, life beyond Earth, is one of the most exciting and profound quests in all of science. It's a journey that takes us to distant exoplanets, probes the depths of our own solar system, and challenges our understanding of what it means to be alive. In this exploration, we'll dive into the conditions necessary for life, the tools and equations scientists use to estimate the likelihood of finding other civilizations, and the ongoing efforts to detect signals from intelligent life forms in the far reaches of space. We live on a planet teeming with life, from the smallest bacteria to the largest mammals. To answer that, we need to understand the conditions necessary for life, the ingredients that make a world habitable. On Earth, life depends on a few key factors, and scientists believe these same factors could be the foundation for life on other planets. The first and perhaps most important ingredient for life as we know it is liquid water. Water is essential for all known forms of life. It acts as a solvent, allowing complex chemical reactions to take place. Water can transport nutrients, regulate temperature, and support cellular structures. Without liquid water, it's hard to imagine life thriving. On Earth, liquid water exists because we are located in the habitable zone of the Sun, the region around a star where temperatures are just right for water to remain in liquid form. Planets too close to their stars, like Venus, are too hot, causing water to evaporate. Planets too far from their stars, like Mars, are too cold, causing water to freeze. But here on Earth we have just the right conditions for water to stay liquid, making it the perfect environment for life to thrive. In addition to water, life also needs an energy source. On Earth, most life forms rely on the energy from the sun, either directly through photosynthesis or indirectly through the food chain. The sun's energy powers everything from plants to complex animals, fueling the cycles of life. But life doesn't always need sunlight to thrive. Deep beneath the ocean, far from the sun's rays, life exists around hydrothermal vents, cracks in the sea floor that release heat and chemicals from the Earth's core. Here, strange organisms live off the energy provided by these vents, showing us that life can exist in extreme environments, powered by sources other than sunlight. This discovery has broadened our understanding of where life might exist in the universe. If life can survive in such extreme conditions on Earth, could it also survive in similar environments on other planets or moons? Another important factor for life is a stable environment. Life needs time to evolve, and for that to happen, a planet must remain habitable for millions or even billions of years. Earth's atmosphere plays a crucial role in maintaining a stable climate, protecting life from harmful radiation and regulating temperature. For other planets to support life, they too would need a stable environment, an atmosphere to shield them from cosmic radiation and regulate temperatures, and a magnetic field to protect them from solar winds. Without these protections, a planet's surface could be bombarded by harmful radiation, making it difficult for life to survive. So what are the chances that other planets have the same conditions that made life possible on Earth? To explore that, we need to turn to an equation that has sparked the imagination of scientists and dreamers alike: the Drake equation. In 1961, astronomer Frank Drake proposed a way to estimate the number of civilizations in our galaxy that might be capable of communicating with us. This equation, now known as the Drake equation, is a tool that helps us think about the factors involved in the search for extraterrestrial life. The Drake equation is simple in concept, but each of its terms represents a deep and complex question. The equation is as follows: n equals r asterisk times f underscore p times n underscore e times f underscore l times f underscore I times f underscore c times l, where n is the number of civilizations in our galaxy with which we might communicate. R asterisk is the rate of star formation in the galaxy. F underscore p is the fraction of stars that have planetary systems. N underscore e is the number of planets per star that could potentially support life. F underscore l is the fraction of those planets where life actually develops. F underscore I is the fraction of life-bearing planets where intelligent life evolves. F underscore c is the fraction of civilizations that develop the technology to communicate across interstellar distances. L is the length of time such civilizations can communicate. The Drake equation is not meant to give us a precise answer. It's more of a thought experiment, a way to frame the questions we need to answer in our search for extraterrestrial life. But even as we consider these possibilities, we are faced with a profound question. If life is common in the universe, where is everyone? In 1950, physicist Enrico Fermi famously asked, "Where is everybody?" If the universe is so vast, and if intelligent life is common, why haven't we seen any evidence of it? This question is known as the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them. There are many possible answers to the Fermi paradox. Perhaps intelligent civilizations are rare, or maybe they don't last long enough to develop the technology needed for interstellar communication. Some scientists suggest that intelligent civilizations may be too far away for us to detect, or that they're simply not interested in contacting us. But despite these uncertainties, we continue to search. The potential discovery of extraterrestrial life would be one of the greatest breakthroughs in human history, and the search itself has led to fascinating discoveries about our own place in the universe. The search for extraterrestrial life is a global effort, with scientists and astronomers using some of the most advanced technology on Earth to scan the skies for signals and signs of life. From radio telescopes listening for alien communications to space probes exploring the icy moons of our solar system, the search is well underway. One of the most well-known efforts is the search for extraterrestrial intelligence, or simply SETI. Since the 1960s, SETI scientists have been using radio telescopes to listen for signals from advanced civilizations. They search for narrowband radio signals, signals that are unlikely to be produced by natural sources, but could be the result of intelligent technology. So far, no definitive signals have been detected, but the search continues. With new, more sensitive equipment, scientists are able to scan larger portions of the sky, increasing the chances of detecting a signal from another civilization. While SETI searches for signals, other scientists are focused on finding exoplanets, planets orbiting stars outside our solar system. Thanks to missions like Kepler and TESS, we now know that planets are incredibly common in the universe. In fact, there are likely more planets than stars in our galaxy alone. Some of these exoplanets are located in the habitable zones of their stars where conditions might be right for liquid water and life. With each new discovery, we get closer to finding a planet that could potentially support life. But we don't have to look only to distant stars for the possibility of life. Some of the most promising places to search for life are right here in our own solar system. Moons like Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are covered in ice. But beneath their frozen surfaces lie vast oceans of liquid water. Both Europa and Enceladus have subsurface oceans that could provide the conditions necessary for life. In fact, NASA's Europa Clipper mission is set to explore Europa in the coming years, searching for signs of life beneath its icy shell. These moons could offer clues about the potential for life in extreme environments, expanding our understanding of where life might thrive in the universe. The search for extraterrestrial life is one of the most profound quests in human history. It challenges our understanding of life, of the universe, and of our own place in the cosmos. Are we truly alone, or are there other civilizations out there waiting to be discovered? With each new discovery, whether it's a distant exoplanet, a strange signal, or an ocean beneath the ice of a distant moon, we get closer to answering that age-old question. And while we have yet to find definitive proof of extraterrestrial life, the search continues, fueled by curiosity, wonder, and the desire to understand our place in the vast universe. If you want to know more about this topic, check out the video. The link is in the description. For nearly 14 billion years, the universe has been expanding and evolving. Stars have been born, galaxies have collided, and planets like Earth have come to support life. But nothing lasts forever, not even the universe itself. As we look deeper into the cosmos, scientists have begun to ask a profound question. How will the universe end? The fate of the cosmos is tied to the forces that shape it: gravity, dark matter, and the mysterious dark energy. Today we'll explore some of the most compelling theories about the ultimate fate of the universe. From the slow, cold death of the Big Freeze to the violent disintegration of the Big Rip, to the potential rebirth of the Big Crunch, each of these scenarios offers a glimpse into the distant future of everything we know. But how will the stars, galaxies, and black holes that light up the universe today fare as time marches forward? Will they survive, or will they meet their own cosmic ends? Now let's discuss this as we journey into the far future and explore the cosmic endings that may await the universe. The universe has been expanding ever since the Big Bang, but how it will end depends on the balance between two powerful forces: gravity, which pulls things together, and dark energy, which pushes things apart. Dark energy is a mysterious force that's driving the accelerated expansion of the universe. But the nature of dark energy is still largely unknown, and it holds the key to the universe's fate. Scientists have proposed several theories about how the universe might end, each shaped by the interplay between gravity, dark energy, and the fundamental laws of physics. One of the most widely accepted theories is the Big Freeze, also known as the heat death. In this scenario, dark energy continues to drive the expansion of the universe at an ever-increasing rate. As galaxies move farther apart, the universe becomes colder and more isolated. Over billions of years, stars will burn through their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. Without new star formation, galaxies will grow dim, and the universe will slowly fade into darkness. The last stars will shine for trillions of years, but eventually they too will burn out, leaving the universe a cold, dark and empty place. In the distant future, trillions upon trillions of years from now, the universe will become a vast, cold expanse where no new stars are born and no energy remains to fuel life. This ultimate state of the universe, where entropy reaches its maximum and all energy is evenly distributed, is known as heat death. It's a slow, quiet end to the universe, a cosmic big freeze. There are other, more dramatic scenarios that could unfold depending on the nature of dark energy. In the Big Rip scenario, dark energy doesn't just drive the expansion of the universe, it accelerates it to the point where the very fabric of space-time is torn apart. In this theory, dark energy becomes stronger over time, pulling galaxies, stars, planets, and even atoms apart. At first, the effects of the Big Rip would be subtle. Galaxies would drift farther apart, just as in the Big Freeze. But over time, the expansion would accelerate so rapidly that galaxies themselves would be torn apart. Stars would be ripped from their galaxies, planets would be torn from their stars, and eventually the force of dark energy would become so overwhelming that even atoms and subatomic particles would be torn apart. In the final moments of the Big Rip, space-time itself would unravel, and the universe would end in a violent, catastrophic event. This scenario depends on the properties of dark energy, and if its strength increases over time, the universe could meet its end in a cosmic disintegration. But what if the universe doesn't expand forever? What if gravity wins in the end? In the Big Crunch scenario, the expansion of the universe eventually slows and reverses. Gravity, the force that pulls matter together, begins to overpower dark energy, and the universe starts to collapse in on itself. Over billions of years, galaxies would collide, stars would merge, and the entire universe would shrink into an increasingly dense and hot state. Eventually, everything, galaxies, stars, planets, would be crushed together into a single point, much like the singularity from which the Big Bang emerged. Some scientists speculate that this Big Crunch could lead to a new Big Bang, creating a cyclic universe where expansion and collapse alternate over eternity. While this idea is fascinating, it remains a speculative theory, and current observations suggest that the universe's expansion is accelerating rather than slowing down. Each of these scenarios, the Big Freeze, the Big Rip and the Big Crunch, offers a different vision of how the universe might end. But they all depend on one thing: the mysterious nature of dark energy. Will dark energy continue to accelerate the expansion of the universe? Will it grow stronger over time? Or will gravity eventually pull the universe back together? The fate of the cosmos is still uncertain, but dark energy will play a crucial role in determining how the story ends. When astronomers first discovered that the universe was expanding, they expected that gravity would eventually slow it down. But in 1998, something astonishing happened. Scientists discovered that the universe wasn't just expanding, it was expanding faster and faster. This discovery pointed to the existence of a mysterious force known as dark energy, which now appears to make up about 68% of the universe. Dark energy is responsible for the accelerated expansion of the universe, but we still don't know what it is. Some scientists think it could be a cosmological constant, a constant energy density that exists in empty space. Others propose that dark energy could be a dynamic field, something that changes over time, becoming stronger or weaker as the universe evolves. If dark energy is a cosmological constant, The universe will continue to expand indefinitely, leading to the slow, cold death of the Big Freeze. But if dark energy is a dynamic force that grows stronger over time, we could be headed for the violent end of the Big Rip. Understanding the nature of dark energy is one of the biggest challenges in modern cosmology. The answer to this mystery could unlock the secret of the universe's fate. While the fate of the universe is tied to the distant future, the stars, galaxies and black holes that fill the cosmos will also meet their own cosmic ends long before the universe's final moments. Let's explore the future of these celestial objects and how they will evolve over trillions of years. Stars, the brilliant beacons that light up the universe, have finite lifespans. Our own sun, for example, is about 4.6 billion years old and is expected to continue burning for another 5 billion years. But eventually all stars will run out of fuel. Small stars like red dwarfs burn their fuel slowly and can live for trillions of years. These stars will be the last to shine in the universe. Larger stars, like our sun, will expand into red giants before shedding their outer layers and leaving behind a white dwarf, a small, dense remnant that will slowly cool over billions of years. Massive stars, on the other hand, will end their lives in spectacular supernovae, leaving behind neutron stars or black holes. But even these remnants are not immune to the passage of time. Over trillions of years, the last stars will fade, leaving the universe in darkness. Black holes, some of the most enigmatic objects in the universe, will continue to exist long after the stars have burned out. These gravitational monsters can consume anything that comes too close, from gas and dust to entire stars. But even black holes aren't eternal. Thanks to a phenomenon known as Hawking radiation, black holes slowly lose mass over time. This radiation is incredibly weak, so for most black holes, it would take longer than the current age of the universe for them to evaporate. But given enough time, trillions upon trillions of years, even the most massive black holes will eventually disappear, leaving behind nothing but empty space. As the universe expands, galaxies will continue to drift farther apart. In the distant future, galaxies like the Milky Way and Andromeda will merge, forming larger, more massive galaxies. But as the universe expands and dark energy pushes galaxies apart, these large structures will grow more isolated. Over time, galaxies will stop forming new stars as the gas needed for star formation becomes depleted. Without new stars to light them up, galaxies will grow dimmer and eventually fade into darkness, leaving the universe a cold, empty place. The universe is vast, beautiful and mysterious. But like all things, it too has a beginning and an end. Whether it's the slow, cold death of the Big Freeze, the violent disintegration of the Big Rip, or the rebirth of the Big Crunch, the universe will one day reach its final chapter. As we explore the cosmos, we are reminded of the impermanence of all things. Stars will burn out, black holes will evaporate, and galaxies will disappear. But in the vastness of time, we are privileged to witness the universe in its prime, a universe filled with light, life, and wonder. The ultimate fate of the universe remains one of the greatest mysteries of all, but one thing is certain: the story of the cosmos is far from over. The universe, vast, beautiful, and filled with wonder. The question is, why does the universe exist at all? Can something as immense and complex as the universe really arise from nothing? Or is there a deeper cause, a hidden reality that transcends what we can observe? Science has made incredible strides in understanding the how of the universe, how galaxies form, how stars burn, and how planets orbit. But when we shift our focus to the why, we step into the realm of philosophy where the questions are no less important, but the answers become elusive. Now we'll explore the philosophical implications of the universe's existence. What it implies about the nature of reality, the possibility that the universe arose from nothing, and the limits of science in explaining the deeper mysteries of existence. The fact that the universe exists at all is a profound mystery. Why is there something rather than nothing? Why does the universe exist, and why does it exist in the way it does, with its specific laws of physics, constants, and structures? The existence of the universe implies that there is a deeper reality at play, one that raises philosophical questions about causality, contingency, and necessity. Philosophers and scientists alike have grappled with these questions for centuries, and they continue to challenge our understanding of existence. One of the fundamental principles of both science and philosophy is causality, the idea that every effect has a cause. In our everyday experience, everything seems to have an explanation. A tree grows because a seed was planted. A star shines because nuclear fusion is happening at its core. But when it comes to the universe itself, we are faced with a profound question. What caused the universe to exist? Some philosophers and theologians argue that the universe must have a cause, something that brought it into existence. This idea is rooted in the concept of cosmological arguments, the notion that the universe cannot be self-caused or uncaused, and therefore there must be an external cause that transcends the physical world. But others suggest that the universe might not need a cause at all. Perhaps the universe is a brute fact, something that simply exists without explanation, much like how we accept that certain laws of physics exist without needing deeper justification. Could it be that the universe just is, without requiring a cause? Another key philosophical concept is the distinction between contingent and necessary existence. A contingent entity is something that could have been different. It exists, but it didn't have to. Earth, for example, exists, but it could easily not have existed. The same goes for stars, planets, and even galaxies. But is the universe itself contingent? Could it have failed to exist? Or is there something necessary about the universe, something that demands that it exists in the way it does? Some philosophers suggest that the universe, or the laws that govern it, might be necessary, that the universe had to exist in some form because it follows certain unavoidable principles. Others argue that the universe could very well be contingent, raising the possibility that there could have been nothing at all. The question of whether the universe is contingent or necessary cuts to the heart of existence. If the universe is contingent, why this universe? Why these particular laws of physics and not others? Could there be other possible universes with different laws, or even no universe at all? These questions remind us that while science can describe how the universe behaves, the question of why it exists in the first place remains one of the greatest mysteries of all. One of the most mind-bending questions in both philosophy and science is whether the universe could have arisen from nothing. Could the vast cosmos, with its stars, galaxies, and intricate laws of physics, truly have emerged out of an empty void? In recent years, some physicists have suggested that it's possible for the universe to arise from nothing, thanks to the strange properties of quantum mechanics. But does this really explain everything, or does it simply push the mystery further down the road? In the world of quantum mechanics, particles can pop in and out of existence seemingly from nowhere. These are known as quantum fluctuations, and they occur even in what we think of as a vacuum, an empty space devoid of matter or energy. Some physicists propose that the universe itself could have arisen from a quantum fluctuation, emerging from a state of quantum nothingness. This idea is rooted in the concept of quantum cosmology, which suggests that the laws of quantum physics could allow for the spontaneous creation of a universe. In this view, the universe didn't require an external cause or a pre-existing entity. It simply popped into existence, much like particles do in the quantum realm. But while quantum cosmology offers a tantalizing explanation for how the universe might have arisen, it doesn't fully address the deeper question. Why is there something rather than nothing? Even if the universe can arise from a quantum vacuum, why do the laws of quantum mechanics exist in the first place? Why is there a quantum vacuum instead of absolute nothingness? When we talk about the universe arising from nothing, we need to be careful about what we mean by nothing. In quantum mechanics, the nothing from which particles emerge isn't really nothing. It's a quantum vacuum, which still contains energy and follows certain laws. But what about absolute nothingness? The total absence of space, time, matter, and even the laws of physics. Can the universe truly arise from absolute nothing? Or is it impossible for absolute nothingness to exist? Some philosophers argue that the very concept of nothingness is incoherent, that nothingness is not a state that could ever exist. In this view, the existence of something, whether it's a universe or a quantum vacuum, might be the only possible reality. Others suggest that there may be a deeper cause, something beyond our current understanding of physics and philosophy, that explains why the universe exists. This could be a metaphysical principle, an unknown law of nature, or even a divine creator. The question of whether the universe arose from nothing or whether there is a deeper cause remains one of the most profound mysteries in the history of thought. Science has given us incredible insights into the workings of the universe. We understand the laws of physics, the forces that govern the cosmos, and the intricate details of matter and energy. But can science explain everything about existence? Are there limits to what science can tell us about the ultimate nature of reality? Science is a powerful tool for understanding the natural world. It allows us to ask questions, make observations, test hypotheses, and develop theories that explain how the universe works. Through science, we've uncovered the laws of gravity, electromagnetism, and quantum mechanics, and we've developed models that describe everything from the behavior of subatomic particles to the formation of galaxies. But while science can describe how things happen, it often struggles with the question of why. Why does the universe exist? Why do the laws of physics take the form that they do? Are there aspects of existence that are beyond the reach of scientific inquiry? There are some questions that may lie beyond the scope of science. Questions about the nature of consciousness, free will, and the existence of abstract concepts like morality and meaning. Science excels at explaining the material world, but when it comes to questions of purpose, value, and existence, it often leaves us searching for answers in the realms of philosophy, theology, and metaphysics. Even in the realm of physics, there are limits to what we can know. The uncertainty principle in quantum mechanics tells us that we can never know both the position and momentum of a particle with perfect precision. The nature of black holes and the singularity at the center of the Big Bang pose questions that challenge our understanding of space and time. Science may one day give us answers to some of the most profound questions about the universe. But as we push the boundaries of knowledge, we may also encounter the limits of what can be explained by physical laws alone. In the end, the deepest mysteries of existence may require us to look beyond science and explore the philosophical and metaphysical realms. The existence of the universe is a mystery that has captivated the human mind for millennia. From the moment we first looked up at the stars, we've sought answers to the most profound questions. Why is there something rather than nothing? Can the universe arise from nothing? Or is there a deeper cause that lies beyond our understanding? While science has brought us closer to understanding the how of the universe, the why remains elusive. The search for answers leads us to the frontiers of knowledge, where science, philosophy, and metaphysics intersect. Perhaps the ultimate nature of existence will remain a mystery, one that continues to inspire wonder, curiosity, and a sense of awe as we explore the vastness of the cosmos. As we ponder the philosophical implications of the universe, we're reminded that the journey to understand existence is as important as the answers themselves. The questions we ask shape the way we see the world and our place within it, and the search for meaning is a journey that transcends time, space, and even the boundaries of the universe itself. Our journey through the cosmos has taken us from the very beginning, from nothingness to everything. We've explored the birth of the universe, the formation of stars and galaxies, the rise of planets and life, and even the possible endings that await the cosmos. It's a story that stretches across billions of years and spans distances so vast that they defy comprehension. The universe began with the Big Bang, an explosion of energy and matter that set everything into motion. From the chaotic early moments of inflation to the cooling that allowed the first atoms to form, the cosmos evolved into the grand structures we see today. Galaxies, stars, planets, and the intricate web that connects them all. We've seen how tiny quantum fluctuations gave rise to the seeds of galaxies, and how gravity pulled those seeds into vast cosmic webs. Stars were born, lived and died, leaving behind black holes and the heavy elements that make up everything, including us. Planets formed in the aftermath, and on at least one of those planets, life emerged, eventually leading to intelligent beings capable of looking up at the night sky and asking, why? But as much as we've learned, the journey is far from over. In fact, some of the most profound mysteries in cosmology remain unsolved. Today, we stand at the frontier of knowledge, with new tools and new ideas that promise to take us deeper into the unknown than ever before. As we peer deeper into the cosmos, we're faced with questions that challenge the very foundations of our understanding. These mysteries remind us that despite our progress, there's still so much we don't know about the universe and its workings. One of the greatest mysteries in cosmology is the nature of dark matter. We know it exists because of its gravitational effects. It holds galaxies together, shapes the large-scale structure of the universe, and plays a key role in galaxy formation. But we still don't know what dark matter is. Is it made of undiscovered particles? Does it interact with other forces besides gravity? Understanding dark matter could unlock a deeper understanding of the universe's fundamental nature. And then there's dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up nearly 68% of the universe, yet we know almost nothing about it. What is this force that's causing the universe to expand at an ever-increasing rate? Could dark energy be linked to the fabric of space-time itself? Or is it something even more mysterious? Another profound mystery is the question of life beyond Earth. Are we alone in the universe? Or is life common across the cosmos? We've discovered thousands of exoplanets, and some of them may even have the right conditions for life. Missions to explore the icy moons of our solar system, like Europa and Enceladus, may provide clues about life in extreme environments. And the search for techno-signatures, signals from advanced civilizations, continues. We've made remarkable progress in understanding the origin of the universe, but questions remain. What triggered the Big Bang? Was there something before the Big Bang? Or was it truly the beginning of time? And what about the end of the universe? Will it freeze, rip apart, or collapse back into itself? The ultimate fate of the universe may hinge on the nature of dark energy, but it's also connected to deep questions about the laws of physics, the role of quantum mechanics, and the limits of what we can know. The next frontiers in cosmology are filled with promise. New technologies and groundbreaking missions are set to transform our understanding of the universe, opening doors to discoveries we can barely imagine. The James Webb Space Telescope is the most powerful telescope ever built, capable of peering back in time to see the first stars and galaxies that formed after the Big Bang. It will help answer key questions about galaxy formation, the evolution of stars, and the conditions necessary for life. With its unprecedented resolution, Webb will revolutionize our understanding of the early universe and the nature of distant exoplanets. Future missions, like the Europa Clipper and Perseverance's search for ancient life on Mars, will continue our quest to find life beyond Earth. The exploration of distant exoplanets will also take a leap forward, with new space telescopes designed to analyze the atmospheres of these alien worlds, searching for signs of habitability and even biosignatures, gases like oxygen or methane that could hint at life. And then there's the ultimate challenge, uniting quantum mechanics and general relativity into a single theory of quantum gravity. While Einstein's theory of general relativity describes gravity and the large-scale structure of the universe, quantum mechanics governs the smallest particles. But these two theories don't play well together. Solving this puzzle could unlock the deepest secrets of the universe, from the nature of black holes to the moment of the Big Bang. The universe's story, from its explosive birth in the Big Bang to its vast, awe-inspiring present, is still unfolding. We've come a long way in understanding the how of the universe, but the why remains one of the greatest mysteries of all. As we continue to explore the cosmos, we're not just searching for answers, we're embracing the mystery, the wonder, and the beauty of existence itself. Every discovery brings us one step closer to understanding the profound story of the universe, and yet with each new answer comes a new question. The journey from nothing to everything has been extraordinary, but the journey isn't over. As we stand on the edge of discovery, the next chapter in the story of the universe is waiting to be written. With new tools, new questions, and new ideas, we'll continue to push the boundaries of what we know, exploring the farthest reaches of space and time, and seeking answers to the most profound questions about our existence.